My name is Ron Buckmire, and the title of my talk today is Math. What is it good for? Absolutely everything. And this is my flash talk for the summer research program for summer 2021. Okay, so here's a brief outline of my talk today. I want to emphasize the fact that mathematics is a human endeavor, and that mathematics has two flavors: theoretical mathematics, sometimes called pure math, and the other flavor of mathematics is often called applied math. And then in today's talk, I will be describing two different topics of my mathematical research: cinematic box office dynamics and numerical analysis. Okay. So the primary subject of my research has been for a while something I call cinematic box office dynamics. And so this is an applied mathematics problem. Applied mathematics are problems that come from where the mathematics comes from the real world. So this is a real world situation that we have movies that are released on screens, and people go see them, and they gross money. And what I'm going to talk about is sort of the mathematical modeling process. And so that involves making assumptions about the approximation that we are going to be doing to the real world situation in order to write down mathematical expressions that describe the real world situation. So here are some assumptions. Movies are released on a number of screens that changes weekly. We have available daily and weekly data on how much money the film makes per day and per week. We're going to assume that the variables involved will be continuous functions of time. And this is a big assumption because really our time is being discrete because we only get time in terms of days, right? Monday, then Tuesday, then Wednesday, then Thursday. But we're assuming that time is a continuous variable. So we would know halfway through Tuesday, we would know at any point in time, we would know exactly what the gross of the movie would be. So here's some variables. G, the cumulative gross, how much total money a movie M has made. S is the number of screens on which the movie M is being exhibited, that is being shown on movie theaters. A is the normalized weekly revenue of M, that is how much money per screen per week is this movie making. So that's A. So these are our primary variables: G, S, and A. And so those are what we call dependent variables. Those are all dependent on T, which is the independent variable time, which is a number of weeks. Okay, so then here are some actual data. And this is Jurassic World from 2015. Probably the better of the Jurassic remakes. And so you can see that as you start, so week 0 is sort of the week it gets released. And this is the number of screens that a movie is released on. And oftentimes it sort of starts as the largest number and it decreases. If a movie is a hit, like Jurassic World was, sometimes the number of screens will go back up, almost 3 months into its run, 12 weeks later, because it reaches over some specific box office total, like maybe it made $200 million, and they start advertising it again to say, go back to see, it was so much fun the first time, go see it again. So this is data on weekly screens. Here's data on weekly revenue per screen. That is the A number, how much money per screen it is making. And what we're really interested in is how much money did it make over time. So the weekly gross. And so this thing started with think 30 million, and then, sorry, 300 million, and then just goes up. And obviously, it's the difference between each cumulative total is how much it made in that week. And the total will eventually level off to some final amount. And what we're interested in, and so this is 18 weeks later, this is how much money it made overall. And this is between $600 and $700 million. And so this is actual data. And so what we want to try and do is come up with a mathematical model, a system of equations that will produce or replicate this behavior of the box office. That's the goal of my cinematic box office dynamics research. Okay, and so what we can notice is that G, A, and S all sort of look quasi-exponential. That is, they have this smooth increase to a asymptote for G, and we even noticed that S also decreased pretty exponentially, and so did A, though it had that little blip at the end. Sorry, S did. And so, right, and you might have noticed that the A and S data is much less smooth than the G data. G sort of, it was very smoothly approaching a total. And our assumption is we observe that blockbuster movies like Jurassic World make the bulk of their final total amount, which we call G infinity, in a brief fraction in the middle. So it was a very steep increase and then it leveled off. And then there's another period where, if you notice, the screens were basically constant in the first 2 weeks. There's what's called a contract period where S is constant. And so we have a fundamental law of cinematic box office dynamics, and that is that the rate of increase of the gross is the number of screens that you're on times the rate at which your weekly rate of increase in box office. So S times A, right? So S times A basically tells you how fast the gross is increasing, which means, and this is a great fundamental law, because if you then want to know G infinity, which is often what you really want to know, how much money is this movie going to make over its total time, it's just the time integral from 0 to infinity of G prime, which is also just the time integral of S times A. Okay, and that's just one of the equations. So it's called a differential equation because it's an equation that has a derivative in it. That's what the G prime means. So the mathematical model I'm talking about is known as the Edwards-Buckmire model. This is work with a good friend of mine, David Edwards, University of Delaware. We say this is a 3D or three-dimensional because there's three equations. There's an equation for G, there's an equation for S, there's an equation for A. We say they're coupled because on the right-hand side, we see that the differential equation for G, S, and A involves G, S, and A on the right-hand side, right? G prime involves S and A, S prime involves A and S, A prime involves S prime, and A. Yeah, so yeah, okay. And so that's the model. And we can solve numerically, as we'll see later, the mathematical model, assuming we have values of particular parameters. So whenever you have a mathematical model, you have assumptions and you have equations, and in those equations, you have what are known as parameters. Those are values of constants which depend varying on what your situation is at the time. And in the Edwards-Buckmire model, there's basically the main parameters are alpha sub S and alpha sub A, kappa, and those are the main ones. Mu is a function that you pick that involves other parameters we don't have to deal with. So here we'll see that we pick some values for alpha sub A, alpha sub S, kappa, and A is basically a measure of, it tells us about the mu function. So here is a result for a sort of frankly horrible movie from 2010 called The Expendables. And if you look at the actual data for G, as you say, it's rather smooth. the curve is the line that the model produces. And so what we're interested in is the computed G infinity over the actual G infinity. And in this case, this is pretty good. The ratio is 1.00794. So that means that the model was just 0.794% or less than 1% over the final gross. Though notice that the behavior is not that great, but the total number, if you're really interested, if you're only interested in G infinity, the Edwards-Buckmire model for many movies will give you good results. But what you'll notice is that if you look at, for example, revenue per screen or A, these dots are the actual, what actually happened. And this green line is what the model is saying. So the model is well below actual data. And then what you'll notice is that screens is above. So you have a low error in A and a high error in S. And so those errors sort of cancel out. And that's what makes G so good. Right, the model assumes that the number of screens, S, was, so the contract period was longer for this movie than the actual number of screens. And this often is the case because exhibitors and distributors enter into contracts to sort of keep a movie on a certain number of screens. But then what happens is that movie theater says, oh, this movie is doing really well. And they sort of, if it's a quick hit, they may sort of add screens early in the contract period to try and sort of get as much money early as possible. So that's our results for G, S, and A for this particular movie. And that's sort of my quick description of cinematic box office dynamics. The next topic I want to talk about is numerical analysis. This is also considered an applied mathematics topic, but it's a little bit more theoretical in that what we're doing here is we're assuming there exists a curve, right? Curves can represent all sorts of real world data, can represent temperature data, could represent the movie data. But we assume that there's an actual function. This is this blue curve, y equals f of x. And we say that its input variables are x and its output variable y. We're going to discretize. We're going to split the interval from A to B into n pieces, equal pieces. So the grid separation, which will be the difference between, say, an x of k and xk plus 1 or an x of k and xk minus 1, we'll call that h, often called the grid separation parameter. And what we're saying is that it's very similar to mathematical modeling. The real situation is this curve, which takes on all values at any value of x between A and B. And we're going to say, well, we don't know the function there. We only know the function at these n discrete pieces. At x of k minus 1, we know we call that value use of k minus 1. At x of k, we call that value use of k. At x of k plus 1, we call that value use of k plus 1. So use of k plus 1 will be exactly equal to f of x k plus 1, or also known as f of x of k plus h. So we're saying that we are discretizing. We're taking this continuous function and representing it as we're only going to know it at discrete values. Okay, and then if we want to, we're going to want to know derivatives of the unknown function f. And if you remember from calculus, there's something called rise over run, or the forward difference formula. If you want to know the derivative at x, you evaluate the function at x plus h and at x, and then divide by the difference, x plus h minus x, which of course is just h. That's called the forward difference because you want to know the derivative at x and you're evaluating the function at x plus h. Backward difference, you want to know the derivative at x, but you evaluate the function at x minus h. Standard difference, you want to know the derivative at f prime of x, at x, but you evaluate the function at a little ahead of it, f of x plus h, and a little bit behind it. So where you want to know the derivative is at the center of your interval, between x plus h and between x minus h. Okay, so that's the continuous versions of derivatives. And then you remember from calculus 1, if you take the limit as h goes to 0, in other words, grid separation becomes nothing, so it becomes a continuous function again, then you'll get the derivative. And so, but we're going to approximate these by discrete differences. We're going to say that h is always a non-zero value, some 0.1, 0.5, some value. And therefore you get discrete analogs of those forward difference formula, discrete difference formula, sorry, backward difference formula, and center difference formula. We call these the discrete forward difference. So instead of doing the y values, we use the u values. If you go back to the graph, so the forward difference is just uk plus 1 minus u sub k divided by xk plus 1 minus x sub k. But since these are varied by h, we know that that difference then will be u sub k plus 1 minus u sub k. These are known as the standard difference formulas. Okay, so what I'm trying to do when I do numerical analysis to solve equations that have derivatives in them, in other words, differential equations, is that, and we only do this for differential equations that we know exact solutions to. And the reason for that is we're coming out with numerical schemes to that will do better jobs of approximating differential equations. If we match it against something that we know the answer to, we can know how well our numerical algorithms are doing. Okay, so what we're trying to do is we take an ordinary differential equation. We know it can be solved exactly, so we can get y of x. That's the exact continuous function which satisfies this ordinary differential equation. We use discrete differences to approximate the ordinary differential equation into what's called a difference equation, or O delta E instead of ODE. If we hopefully can solve the O delta E, the difference equation, exactly, and we get discrete values y sub k, which in our graph we would call these u sub k's. But u sub k is really y of x evaluated at some discrete value x sub k. And so what we're trying to do is the blue is the exact solution of the difference equation, and the red is the discrete version of the exact solution of the differential equation. And our hope is that these two things are approximately equal to each other, and we want to make this difference. We want to make this green approximation sign as small as possible. We want the discrete solution to the exact differential equation to be as close to the exact solution of the approximate differential equation, also known as a difference equation, to be as close to each other as possible. If we can make them exact, then we know our difference equation, our numerical method, would be exactly solving this differential equation. And that's really the main idea. I'll show you some specific examples of how I do this. We use some new kinds of difference schemes to approximate the differential equation called a non-standard finite difference, or Mickens discretization. Ronald Mickens is an African-American physics professor at Clark Atlanta University, and he came up with this idea of why use standard finite differences. Think about different ways that one could discretize or approximate derivatives. And he has this whole mechanism for doing that. So instead of just dividing by the difference, the grid separation parameter, use a function of the grid separation parameter that gives you behavior that you're interested in. And here are some examples of different kinds of phi sub h's. H is obviously the most boring one. That's the standard finite difference. But what you want is this h function, this phi, or this denominator function, to have the behavior that when h gets really, really small, the limit as h goes to 0, that all of these will actually look like h. So they will also go to 0. So the limit as h goes to 0 of h is obviously 0. Limit as h goes to 0 of sine of h is sine of 0. So that's 0. Limit as h goes to 0 of e to the h minus 1. That's e to the 0, which is 1 minus 1, so 0. So all of these have this behavior that as h goes to 0, they also go to 0. But they go to 0 at what we say is big O of h. They look like h. And so here's one example of a non-standard finite difference scheme. Remember before we had the derivative was yk plus 1 minus y sub k over h. In the non-standard version, it'd be y sub k plus 1 minus y sub k over phi of h. And here we decided to use phi of h is e to the h minus 1. And we're using this denominator function. And that ends up being actually an exact non-standard finite difference scheme for a very simple differential equation, but it's just sort of proof of concept that this can happen. And then, so to conclude, I showed you 2 examples of my applied mathematics research. I described mathematical modeling in the context of cinematic box office dynamics. And then I described what numerical analysis means. That's where you convert a continuous problem to a discrete problem. You solve the discrete problem exactly, and then basically you repeat your solution of your discrete problem, making h smaller and smaller. So instead of h being, say, you split your scheme into, say you split your interval into 100 pieces from 0 to 1, that's each piece would be 1 over 100. Then it might be 1 over 1,000, then maybe 1 over 10,000. So h is getting really, really small. If it was continuous, as h goes to 0, it would be a continuous problem. But since we're dealing with discrete values, h can get really, really small, but never actually be exactly equal to 0. And so hopefully that gave you a little flavor of what math is good for. Math helps us solve problems. The people who solve these problems are humans. People who do math, so humans do math. Math is a human endeavor, and mathematics is for solving problems. Thank you very much.